Good morning, everybody, and welcome to the second session of this week. We're still dealing with electricity, with the DC circuits, basically. Last time when we started this, we were actually discussing we started with Ohm's law, and then we actually went into the lab. And when we went to the lab, we discussed more in detail what the current is, what the battery is, and actually we had hands-on approach to them. In a sense, we saw what the battery actually looks like. We saw also the different kind of resistors. Some of you actually were aware of the color coding on the resistors and what that means in terms of determining the value of the resistor. Turns out that the ones we were using in the lab, they were 470 ohms. So, and the power supply at that point, which is the equivalent of a battery, was delivering 6 volts of battery. You had multimeters actually testing those batteries and giving you the correct power. And then when you put them in parallel, basically you take 2 batteries and you put them one next to one another, it makes 12 volts because you have 6 and a 6, which is and adds up to twice as much as it was before. And then you were also using the ammeter, which is a device to measure the current in the circuit. And you had also light bulbs in there. And you saw the effects basically on what happens when you take light bulbs and put them one next to one another. In that case, the light actually dims a little because the current drops a little compared to when you take only a single light bulb, for example, or when you put them actually in parallel. So today's discussion actually is going to be a little bit more in detail about these things. And we're going to finish this chapter. And we're not going to start chapter on the magnetism until next week. Next week is going to be an exam week, meaning that on Wednesday, a week from today, we will have our exam. The exam is a 2-parter. It has 2 components in it. The first component is going to be on Wednesday, October 9th. November 9th. I'm sorry, it's not October anymore. We are in November. So it's going to be November 9th, which is a week from today, is going to be our conceptual part, which is part 1 of the exam. And then there is another component to the exam, which is component number 2. And component number 2 deals with the problems that I gave you a sample of them last time when we had the discussion session way back in October. Now it sounds like it's a long time ago. It's only about 2-3 weeks ago at most. And some of them actually we discussed them a week later, and I actually posted them for you guys also on Canvas. And we went through the entire series. We discussed it in detail. Some of you, during the lab session last Monday, 2 days ago, they were wondering about some of those problems because they were not clear on them. And I urged them, and I continue to urge you guys to please reach out, okay? It was not convenient to dedicate another session in the lab because your lab, as you guys noticed, ran for a long time. Actually, we did not even finish the second part of the lab. So we could not have done those problems on that day, but please reach out. Let's have a one-to-one session meeting, either online or in person on campus, so that we can hammer these things and it's clear to you. The second component is going to be on November 10th and November 11th. So it's going to be on a 2-day window. So you will have Thursday, because we really don't meet on Thursdays for this class. So you may have other classes or work or have other plans. So you still have Friday. So there is actually a 48-hour window for that part, which deals with the components dealing with the problem sessions. Again, the problems are going to be from a data bank, in a sense that not 2 of you will have the similar problems. Furthermore, they are going to be based, at least the ideas based on what was discussed in class. So if you did all of the reviews, you should not have any difficulty with doing these problems, and you should sail through it. Now, exam 3, which is apparently coming immediately after Thanksgiving, that will also have a component in it, because I was thinking that we will have a chance to do exam 4 and then probably the final. Now it doesn't look like we will have that. So exam 3 will be immediately after Thanksgiving, followed by the final. The final will be comprehensive, and exam 3 will have a component in it that is also similar to exam 2. but the final is actually all comprehensive, the entire thing, and it's all conceptual. So again, exam 3 is going to be a similar fashion. Immediately before Thanksgiving, we will have a dedicated problem session. It's going to focus on electricity, okay, and magnetism. So those are the two topics that we're going to be dealing with the week before Thanksgiving, because one of you guys were asking during the during the lab also, are we going to have another session basically dedicated just to the problems during the lab session? And he said yes, and actually it was planned apparently already on the syllabus. So consult the syllabus, you will see exactly the date when we're supposed to be meeting, and that date is going to focus mainly on electricity and magnetism, which is not the topic of this exam 2. It's going to be exam 3, actually. That's where we're going to have that. In addition to quantum mechanics, that is also going to be part of exam 3 and also the final. In the discussion also, I noticed some of you guys were talking about the multiverse and the parallel universes and things like that. There is actually, after Thanksgiving, we still have to deal with quantum mechanics. And we're going to discuss then and there the double slit experiment, because part of it is a light behaves as a wave. It turns out that also particles behave as a wave, and that can actually hopefully shed some light on these things that you guys were talking about. Not everybody, there were a group of you guys, the group that was sitting right in front of the structure desk, basically, where I sit. So that group, they were talking among themselves about the multiverse, and the ones who were having, they brought a lot of coffee for the lab. Anyway, so we're going to have a discussion on that, and it's going to be part of quantum mechanics, which is actually a required part of the component. So it was not like something that I added at last minute just because I saw you guys. But now I remember that it was part of the discussion, so we're going to build on that. Anyway, so this is basically where we are today again. So let me share with you the screen. And let me find my notes, and here they are. So we're still dealing with chapter 21. Let me click anywhere outside and back to it, just to give me where we stood last time. So last time, basically, we introduced Ohm's law, and that is what we used, okay? So this is known as Ohm's law, and it's something that is worth remembering. So if somebody asks you, what did you learn from this class? Of course, you're going to tell them I learned F equals to ma, which is the big deal. Forces cause change in motion. So this is a big deal. So this is something that you need to remember from this class. And that was the part that has to do with mechanics. Obviously, we talked before about the waves, but we really, I mean, wavelength, frequency, and all of that. And those are concepts that are worth remembering. However, this is by far the most important thing that you're going to take from this class. Force is equal to mass times acceleration. This is Newton's second law. Probably the next thing that's probably worth remembering from this class, the next thing in importance is Ohm's law. This is Ohm's law. And again, you have a cause and effect relationship in here too, where the voltage is the difference in potential between 2 points. This is the current, and this is the resistance. So this is for circuits. Usually, the way this law is actually written is A equals to F over M, meaning if you have a force, there is an acceleration, which is change in motion. How is that gauged? How is it big or small? How is it basically tempered? Is by the mass. If you have more mass, less acceleration. If you have less mass, you have more acceleration. So the inertia determines in here the response. So again, this is the excitation. This is what causes the whole thing to get going. And this is the response of the system. The response, how big it's going to respond, if you wish, to that external agent, to the cause, in this case, it depends on how much mass the system has. So in a sense, this is the cause, and this is the effect. So this is a cause and effect relationship between mass and acceleration. Same thing in here. If you have a voltage, you're going to have a current in a system. How big the current is depends on the resistance. So again, this is your cause, and this is your effect. And what tames that, what tames the current, is the resistor. That's it, the resistance. The more resistance you have, the less current you're going to have in the circuit. So in a sense, M, the mass, is the resistance to the change in motion. Okay, change in velocity. Would the velocity change at all? M will determine how much that change will happen. Of course, the change will happen if you have a force. The same thing. R, in this case, the resistance is actually a resistance by itself. So it's a resistance to the current. And the current is the change in charge. Okay, so there is this one-to-one correspondence between the two. Obviously, the units for the resistance is different than the units for the mass. The unit for the mass, if you guys remember, is the kilogram. The unit for the resistance is, in honor of Mr. Ohm, it's ohm, and it's written capital omega. So this is the Greek letter omega. But it's read ohm. You don't call it omega. You don't say I have 470 omegas. This is not correct. You say I have 470 ohms. And you write it actually, that's the resistor that we found in the lab, 470 with a capital omega. Okay, the Greek letter omega. So that's basically the comparison between mechanics, which is this part. This is mechanics. And this is electricity. Okay, so there is a cause and effect. Forces cause change in motion. Voltage difference, actually. This is not, I mean, we write it V, but what we mean by it is that there is a difference in potential somewhere. If you take the battery, for example, so this is we have a battery. I thought I saw one. Yeah. Here is a battery. If you're careful enough, you should see on one side of it, it says positive. On the other side, it's negative. So it has two terminals. This terminal is positive, and the other terminal is negative, which is this whole black area in here. It should have a minus sign somewhere in here. But of course, if we know what the positive is, we know what the negative end is. So this is the negative end. This is the positive end, and that you connect the two, and now you have a battery. So in this case, we are interested in actually how big this potential is compared to this potential. We don't care what this potential is. We don't care what this potential is. We don't care at all what they might be. This will be a billion. This will be a billion and 1.5 in addition to that billion. That's a 1.5 battery. 1.5 volt battery. If you have this one is negative 12, this one is negative what? 10.5. So if I subtract 10.5, negative 10.5, deduct from it negative 12, I will end up with again 1.5. So it doesn't matter what the voltage is in a given point. What matters is the difference between the two. That's really what matters. That's what the battery does. Okay. So let me go back into my notes. So again, think of this battery that it has two terminals. One of them is usually labeled positive, and one of them is labeled negative. What matters is the difference in potential between this one too. So this is where I usually we put a delta V. It's just because we get lazy in here in Ohm's law, and we drop the delta, understanding that this is really what we mean in here. Please put it in for us because we're lazy. That's all. Okay, so V equal to IR is not necessarily the potential at a given point is equal to the resistance. The resistance between what and what if it's the same point. So now it's actually the difference in potentials. So this is how the symbol is. So Ohm's law really should be delta V equals to IR. The change in potential or the difference in potential is the current that is flowing between the points where the potential is taken. So this is point 1, this is point 2, and let's say there is a current flowing between them. And that current is I, and let's say there is a device in between those two that has a resistance R. Then in this case, the difference in potential between 2 and 1. So this is, let's say, for example, 1000, 1.5. And this is 1000 even, then the difference is exactly, and in this case, V, which is really a symbol that I meant by the delta V, the difference between them is 1.5 volt. I don't care what the potential is in here. I don't care what the potential in here is. All we care about is what is the difference between the two. If there is a difference, in this case, there is clearly a difference. They are not the same potential. And that difference is exactly 1.5 volt, like this battery, exactly 1.5 volt. Then, hey, then if there is a resistor, let's say, for example, 470 ohms, like the ones that we were dealing with, I will have a current. And that current is going to be 1.5 divided by 4.7, 470, I'm sorry. And it's going to be a small current, but nonetheless, it's going to be a current. So this is a voltage, this is in ohms, and the answer is going to be in amps. So just let me do this calculation here. I know it's not really the point that we're trying to convey in here, this number, but I'm just trying to give a sense of what these things are written. So let me get the calculator. So what I said in here is I have 1.5 volt divided by 470 ohms. And the answer, of course, is a tiny 3.2 amps, milliamps. Actually 0.03, yes. So it's tiny current, of course, has 3.2 milliamp or 3.2 times 10 to the negative 3 amps, okay? So that's the current that is going to be flowing in this case. So it's a small current, it's in a milliamp, but it's a current nonetheless. So that's basically how you use Ohm's law. Obviously, for our case, we're dealing with a battery that has 6 volt. So if you look at the batteries that we were having, the battery that we have actually is kind of a transformer. So it's connected to the power supply that is draining 120 volts from the power supply, and then delivering, and it's AC current actually going at 60 hertz. So it's changing current like this. And it was delivering to us a steady current of 6 volts. So this point in here is higher than this point by 6 volts. This point could be, for example, 120 volts for all we care. This point is 126 volts. This could probably be 80 volts. And if it's 80 volts, this is not 126 anymore, it's 86 volts. That's what that battery was doing for us. Okay. So that's all there is to it. So all we care about for that battery, when you put the multimeter, so you took one end of the multimeter device here, and the other hand in here, and you turned the dial, the knob, you turned it toward where it says, okay, I want to measure volt, and I want the tolerance to be up to 12 volt, because if there was a setting for 3 and 12 and so on and so forth. If I set it at 3, it's going to be off the chart. The needle will go all the way to the end because it knows it's more than 3 volts. But if you know that the answer is less than 12 volts, so you set it to 12 volts and the needle went to the middle. It was reading exactly 6 volts. So just to remind you, it was a big bulky device that everybody was commenting from. Where did you find this one? And it looks like it's an antique device, and it's probably true. So you had to move the dial in here to 12 volts, And when you looked at the screen was giving us a reading in this line in here between 0 volts all the way to 12 volts, somewhere in the middle, and here where it was 6 volts. So that's the voltage in here. So this dial is just to tell you the tolerance of the device, either 3 volts, 12 volts, and I think it had like 90 volts. I don't remember the rest of the figures, but the point being in here is just the, excuse me, I have something on my watch in here. I'm trying to read the message in here. It's nonsense stuff. Anyway, the point being in here is that is Ohm's law for you guys. Ohm's law is the equivalent to F equals to MA. Okay. So this is important thing. The other thing also that we discussed is the power. So the power we said is equal to the current times the voltage in a given device. One more thing before I forget in here, okay? When you guys were using the ohm meter, you could connect it directly to the battery. I could have a multimeter, I actually have one downstairs. You could connect it to the battery, and it's going to give you a reading. If the battery is still good, it should say for this one, 1.5 volts. If the battery starts to drain, it's probably going to read less, 1.4, probably 1.2. And if it's by the time it's 1.1 volt, this probably will not be useful. You're going to replace it because it drops so much that it's not going to be a good battery anymore. Obviously, if it drops to 0, it's just like air. You take basically a multimeter and you connect it in the middle of the air, and that's not a battery. So otherwise, we will have electricity everywhere. So again, there is no, it's like an open end. It's like basically take a wire and you cut it in two and you're trying to measure the difference between the two ends. In this case, there is no difference in potential between one end and the other. So, or it's a wire actually. Even a wire, if you take the both ends, it should not have any potential difference whatsoever because there is no power in it whatsoever. So that's really the one thing. But if you take it, for example, across a resistor, then it matters. So when you did the same experiments with the power supply itself, we were always getting 1.6, getting 6 volts on it. But when we took it across a resistor or across the light bulb, that will only have a reading and only then when there is a current flowing. Then it's going, if this resistor is R, and if the characteristic of this light bulb is R, and there is a current, then what you were reading is IR, the current times R, and that was the voltage also. But if you kill the current, if you turn the switch off, then in this case, there will be no reading in there. It drops to 0, back to 0. But across the battery, it doesn't matter because it's always sustaining that difference in potential across its terminals. Now, when we discussed also last time, we discussed the power, and the power also is related to the voltage via this relationship, meaning this is the power. This is what we have discovered in mechanics. Actually, this is the power, and the power is in watts. That's the unit for the power, or joule per second if you really care about it. So this is in honor of Mr. Watts, who did a lot of Mr. Watt actually, who did a lot of work in this area, and this is in honor of Mr. Joule. And if you remember, the energy is actually force times distance, and the force is kilogram meter per second squared times distance kilometer per second divided by second squared, and divide this whole thing by another second. So the power actually is a kilogram meter squared by second cubed. So this is watts. So if you want to, this is all in terms of the mechanical stuff. This one is actually in amps. An amp is just a fundamental unit, just like anybody else, times the voltage, and the voltage has the units of, remember, V equals to IR, or, and then you have the ohm in here. So you could have that in terms of the current also, and in terms of the ohms is the voltage over the current, but there is another way of finding the difference between these two using this relationship. If you guys remember, if you take the voltage and you multiply it by the charge, you're going to find an energy again. This is the potential energy. Remember when we defined in the previous chapter that the electric field and the force are related to this expression? This is the force in Newton, this is the electric field in Newton per Coulomb, and this is the Coulomb. Now the same thing, turns out that the energy, also discussed this one last time, which is in joules, this is the volts, and this one is actually the charge, which is in Coulomb. So again, this one I could express it as a joule per Coulomb, and a Coulomb and an ampere are related to one another. Remember, the current was the rate at which the current charge is changing with respect to time. So the current, or the charge in this case, the units for charge, which is the Coulomb, by the way. So I'm going to put this entire thing in units, symbols. So this is the Coulomb per second, because the charge rate of charge per unit time, and this is the ampere. So this ampere, which is really a fundamental unit, can be written as a Coulomb over second, and a Coulomb cancel Coulomb. And now I have a joule over second again, and that is a power. So the units match, the mechanical units and the electrical units match. And joule over second is the units for power, which is watt. So this is again the watts. So in terms of units, everything matches, which is a very, very important point in here. And it's true all the time. It's not just today. It's true all the time. When you come up with a relationship, it doesn't matter what relationship you come up with in physics, always try to make sense of the units. They should match from one side to the other. This one is in watts, which is a joule per second. And I just said that this is IV, and IV is an ampere times voltage, and an ampere times a voltage. And if I use this expression for the voltage, which is this one, this expression. So the voltage is an energy, which is a potential energy. So this is the electrical potential energy. That's the symbol we used actually, EPE, but it's still an energy nonetheless. So it's still in joules divided by Coulomb. So this is a joules by Coulomb times an ampere, and an ampere itself is a Coulomb per second. Cancel the Coulomb with this Coulomb, and I will add left with the joule per second. And joule per second is exactly the same expression, which is the watts. So the watts on one side and the watts on the other side, they match. This is an important skill. I know it's not a big deal right now for you guys, but later on, some of you are actually transferring to the calculus-based courses, so we are doing your prep for that. This is actually going to be chapter 1 of Physics 202. The first lesson that you're going to have, among other things, is you do what is known as dimensional analysis, making sure that the dimensions match. I know one of you guys approached me about that because trying to find exactly what section next spring is going to be offered for 202, and at least I know that I'm doing section 1, and there may be other sections of 202, which is the calc-based version of this class, which is the prepare you for engineering classes and things like that, or transferring as physics majors or chemistry majors and things like that. Anyway, so if you're not doing that yourself, it's a good thing to know that dimensional analysis works. That if you're measuring something in one thing and you're saying it's equals to something else, the other thing must also have the same dimensions, must be the same thing. So if you're compare apples, you better have apples on the other side. You cannot have oranges on the other side. That's what that means, okay? So this is basically the power. For the case of the resistor, this is easy. For the case of the resistor, the power is equal to I times the voltage, and the voltage is I times R. This is Ohm's law. This is what V is for the Ohm's law. So for the case of the resistor, this is easy. The power is the resistance times the current squared. Obviously, the power company doesn't charge you. I mean, the power company, when I mean power company is the electrical company, they don't charge you by how much power your device can have. That is just its power, how much it's going to consume per second. It's going to charge you for the energy. And the energy that the power company is going to charge you for is usually the power times time, if the power is steady, constant. Most devices have a steady constant consumption of power. Like a light bulb, for example, you go to the store and say, you know what, I need a 100-watt light bulb. Or you would want to have another light bulb, which is 40-watt light bulb, okay? Then how much power, how much energy you're going to consume, it's not 100 watts or 40 watts. You could have this one for, let's say, for example, 1 hour, or let's say, for example, 10 hours. just to make the number round. So this is 1,000 watts hour. That's how much you consumed. The power company doesn't usually measure in this watt hour, it measures in kilowatt, which is 1,000 watts. So the power company will charge you for a kilowatt hour, for 1 kilowatt hour, which is typically about 15 cents or 20 cents, depending on the power company, and depending also on the time when you used it. If you use it during peak hours, they charge you more. If you use it during less peak hours, then you're going to be charged less. Anyway, so that's one thing. But if you take this one, for example, and you have it lit for 100 hours, well, you can do the math. 100 times 40, that's 40,000 watts hour. And 40,000 is 4 kilowatt hours. So the mere fact that you have a 40 watt light bulb doesn't mean that you're going to be charged less than a 100 watt light bulb. It depends on how long you have it on. Obviously, this one is only for 10 hours. This one is for 100 hours. This is left for forever. Okay, so at the end of the day, it's going to be charged more for it. That's really what that boils down. But if you put them side by side and you see how much you're going to be charged for them, let's say you let them for 10 hours each, then in the first one, it's just 1 kilowatt hour, depending on what time it is. It could be anywhere between 14 cents all the way to probably 27 cents, depending on the power company. And this one, if you let it for the same amount of time, which is 10 hours, 10 times 4, that's 400, which is less than a kilowatt hour. And the rate is you're going to multiply by the rate. So it's going to be what, 14 times 0.4, 4 times 4, that's 16, 4 times 1, that's 4. So it's going to be 4.6 cents. Or you do the math for the other one. 4 times 7 is what? 28. 4 times 2 is 8, and 2, that's going to be 10.8 cents. So yeah, it's going to be charged less for the same amount because I got this number by multiplying 40 times 10. So I left both of them running for 10 hours. The first one will give you exactly 1,000 watts hour. The second one will give you instead 400 watt hour. And of course, the power companies, I was saying, charge you by kilowatt hour, not by watt hour. Okay, 1,000 watt hour if you wish. So that's how this numbers work. At least typical power companies probably have new ones that might charge you with. No, the price is going up. Probably they will be charging you with 100 watt hour, something like that. Anyway, so this is some of these things that you have a sense of. This is something also that you go and watch your bill for. Obviously, the power company charges you for all the things too. They charge you for subscription, and charge you for taxes, and they charge you for all the things. So at the end of the day, you will pay more than 27 cents, even if you have no light on, or if you have no other device running on. Your computer, your cell phone, they use more or less powers. Okay, so you have, for example, the charging station of your cell phone could be a 5 watt. So in that case, depending on how you have your cell phone charging, or your car, for example, charging. If you have a Prius, for example, it's 7.5 kilowatt to charge it from empty to full. A Tesla will require more power. So again, that stuff is out there. Okay. So this is something that is that we covered last time. So the last 2 points that, and again, we discussed them in the lab, honestly, and we had 2 actual divisions in the board that we were using. The upper division was all of it in series. The lower one was all in parallel. And I made a note in the lab of the fact that the power company delivers your power to your home, all of it in parallel, because of the fact that all of the plugs are 120 volts. Okay, and that was part of the discussion, by the way, where you're supposed to compare parallel to a series and see the difference between them. And based on what we did the experiment, which one has advantages, disadvantages, and of course, in a real circuit, all of them are present. So you could end up with a branch that has series stuff, but it's a branch of another parallel stuff, which combines later on to be part of a series of another thing. So you could end up with stuff that is, for example, you have a resistor, you have a capacitor, you have an inductor, you have other things chips, for example, they're all in series, but it's all part of a branch of another device in here that has probably a resistor. But this entire thing could be just another component of a on series with another one or more than one. And then this probably will branch into 3 components. Okay, and this will branch into 2 components. So you could have a parallel in series with another component in here, but it's the entire thing is part of a parallel with another component in here, and both of them are actually parallel with another thing in here. But the entire thing is just in series with a small device, which is actually in series with another branching in here of 2 components in parallel. I mean, 2 branches in here in parallel. One of them has 3 components in series, and another one has only a single component in it. And both of them are in series, basically in parallel, and in series with this one, but also they're in series with another one. The whole thing could typically be kind of a long, basically, chain in here. So typically, you have 2 branches that you can break them down to either parallel or series. Typical example of a parallel is, for example, we have let me write the battery. Remember, we did in the lab, we discussed the battery and how the symbol for it. The battery has a negative node and has a positive node, a negative terminal and a positive terminal. In electronics, in electricity, usually the shorter node is kind of bulkier, but shorter, and that is where the negative node is. That is where this end of the battery is. Okay, and the positive, which is this end, is where the longer leg is. So I have a component in here. And to repeat the stuff that we did in the lab, we're going to just have the same values. Obviously, there is another thing that I forgot to include in the picture, and that was something that we had in there, and that was the switch. We needed the switch in here, remember? That's part of the component. So if we have the switch open like this one, nothing is going to happen. But when we close the switch, then in this case, current start flowing. And I took, I think, a 10 ohm in here, and I took 20 ohm in here, resistor, and I took this battery to be typical of what we were dealing with. In the other scenario, again, we have a battery here that was 6 volt also. If I don't write the plus or the minus, it's assumed just from the shape. And then I have also a switch, and I have a resistor again of a 10 ohm, followed by 20 ohm resistor, and both of them are connected to the battery. Okay, and the fact that they have a 6 volt in here, it's the same voltage in here, and it's the same voltage in here when this switch is closed. So I need to close this switch at some point. So this is a regular switch. There is actually 2 kinds of switches. There is the switch, which is this one, and there is the two-way switch, basically an AB switch. You turn it on one side, it's off, but you turn it is going to be either close one circuit and open the other, or close the other and open the first, or close both of them. Well, I mean, open both of them. So that's called an AB switch. Okay, so there are different kinds of switches out there. So this is a regular switch, the one that you turn on and off the power with at home. Okay, so again, you have a 6 volt in here. This entire wire, when it's closed, is the same wire. So the voltage is the same everywhere in here. It's the voltage across the battery. So if this happened to be 86 volt, this entire line is 86 volts. And if this is 86 volt, so that better this one be 80 volt, okay? So this entire line is 80 volt. So the difference in potential between this point, which is 86, and this point, which is 80, is 6 volts. And the difference between this point in here, which is 86 also again, because this entire line in here, when it's connected, is the same voltage. And this entire line in here everywhere is 80. So in this case, then also it's 6 volt. So that's the key thing in here. The voltage or the drop in potential is the same. Drop in potential is the same. Okay, that is the key thing for a parallel circuit. So this is one point in here. Versus in the case of this one in here. So if I have a current when it's closed, the current will leave the battery. So again, doesn't matter if this is 86 volt and this is 80 volt. That means this is 86. This entire line is 80. I'm sorry. And this entire line up to this one, when the switch is closed, of course, is 86. But this point in here could be anything. We'll find it. Okay, this point we'll find it. But at this point, this entire line in here is 86. So there is a 6 difference between the. That's what the battery does in this. It could be. I'm not saying it's 80. This is just a hypothetical. So it could be 70 for all we care about. If that's the case, then this is 76, and this is 76, and this is 70. Okay, what matters is the difference. We don't care about the single value. What matters is how big is one versus the other, and that's what the battery does. So that battery in the lab was doing 6 volts. So it doesn't matter. So the fact that the power company is telling you have 120 volts in your plugs, it doesn't tell you what the plug is. Each end of the plug is. No. Then you don't care. Nobody cares. So all you matter is the difference between the two. Okay, that's it. That's the key difference between it and F equals to MA. So now here is the thing about this one. If there is a number of charges that leave per unit area, per unit time, which is the current, that charge is going to end up in here and is going to emerge because of the conservation of charge. So it's the same current everywhere, and it's the same current in here. So the difference between this one and the other one, so the current is the same everywhere. Current is the same in a series configuration. So that is one big difference. The voltage drop in here is the same. The current here is the same. That's one distinction. Let's find the current in here since it's not the same. Well, the voltage difference in here is, if I take a voltmeter, I will find it reading 6 volts. 6 volts must be equal to the current that is flowing in here times the 10 ohms. So I have 6 volts is equal to 10 times the current that is flowing in this section. And I'm going to label it as current I1 if you want to. I'm going to find its value. Its value is simply 6 over 10, which is 0.6 amps. So this current is 0.6 amps. How big is this current flowing in here? It's the same idea. I have a 6 volt difference between this point and this point. So 6 volts must be equal to that current times the resistor, which is 20 ohms. 20 ohms times that current. And that current then is going to be 6 over 20. And that is going to be 3 over 10, which is 0.3 amps. So this current is 0.3 amp. So how much current did we already have in the circuit to begin with? Remember, I have a current in here that's split into 0.6 and 0.3, so it must be 0.9 amps. So the current that comes in here, it's a 0.9 amp. The vast majority, or twice as much, 0.6 amp will go this way, and half as much of this number go through the other one. So the path with the least resistance will have higher current in it. The 10 ohms is less than 20 ohms. So the path of least resistance will have a higher current in it. So, but the two currents are the same because this node in this point in here, remember, charge is conserved. It does not create charges. It's not all of a sudden you'll have more current coming out. No, it doesn't all of a sudden eat some of the charges. It does not keep them either. So if a 0.9 amp come in, which is the number of charges per unit time, that's what the current is, they split. And how do they split? They don't split equally. They depend on the path with the least resistance, that where the vast majority of the current will go. So in here, the current splits, where in a branch, of course, in the branch, following the path of least resistance. In this example, when they split, I have 0.9 amp. 0.6 amp will go to the 10 ohm, and 0.3 amp will flow to the 20 ohm. So the 20 ohm, the higher resistance, will have less current in it. Okay. In this scenario in here, the current is the same. Whatever it is, it's the same. But, and how much it is, it's easy to find. Actually, the current is easy to find. All you have to do is divide the 6 volt by the entire resistance in here. So how much current we're going to have in this case? Well, remember, I have 6 volts, and this is going through a 10 ohm and 20 ohm times this current. 10 plus 20 is 30 actually ohms, and times the current. Obviously, the current is 6 over 30. 6 over 30, so it's going to be 1/5 or 0.2 amp. So 0.2 amp in this scenario is going to go through the entire current, because there is no place for it to accumulate, and there is no place for it all of a sudden charges starts to appear. So in this case, the current is the same, and it is actually, for my example, in this example, it's 0.2 amp. In a different example, it could be a different thing. But the voltage drop is different now, because think about it. Between this end and this end, I have a current that is running of 0.2 amp. And if I use Ohm's law, if I take an ammeter and read between those two ends, I must be reading 0.2, that's the current, times the resistance, which is 10. So it must be 10 times 0.2, so I must be reading 2 volts. So there is a 2 volt drop from 76 down to something, so that I drop by 2. So this point must be 74 volt. Again, this is an example. I'm not sure if exactly, nobody cares what this point in here is, but there is definitely a drop of 2 volts from whatever this value is to this point in here. Had this been 76, then this must be 74 volts, so that there is a drop of 2 volts. And from here to here, we must have a 4 volt drop, because we dropped by 2 from 76. So we must drop another 4 to make up for the 6 volt difference. And it's easy to check also. Remember, we have a 20 ohms. The current is the same. It's 0.2 amps that runs through both of them. And 20 times 0.2 is exactly 4 volts. It's exactly what the doctor ordered. So it drops by that same 4 volt to drop back to 70. So it was 76 in my hypothetical example, which nobody cares about at this point, because we don't care about the voltage in a specific point. All we care about is the difference in potential. And that's what we were able to calculate, honestly. And that's what the device will measure. So if you take a multimeter and put the red terminal in here, and you put the black terminal in here, and you put them like this, and you watch the needle, and the needle will move toward the 2 volts. What it's telling you is the difference between those red and the black is 2 volts. And if you take the same multimeter and you connect the red in here and the black in here, and you read it, it's going to move to 4 volts. If you add 2 plus 4, it must be the same thing as you put it between the battery's terminals, 6 volts. So the voltage is not the same. That is, so this is 1 in here. So this is 0.2 in here. Voltage drop, add up to the total voltage. Higher resistance have higher voltage drop. But the current is the same. Higher resistors have higher drop in potential. Okay, it's very important to remember the following. If you somehow open the circuit, you open this point, and you measure with a voltmeter here, you're going to find 0. Why is it 0? Because there is no current anymore flowing. And the voltage is supposed to be 10 times the current, and there is no current when you have the switch open. So the voltmeter should read 0. The same thing between this point and this point should be 0. And the same thing between this point and this point, it should be 0 because the switch is open. However, if you put it in here and any point in here, it's going to read 6 volts because you're going across the battery. The battery is still good. It's still making 6 volts. But whether you're going to drain current from it or not depends if the switch is open or not. Okay. The same thing in here. If you read the switch, the value in here, you're going to find 6 volts. But in here, there is no current flowing, so it should be 0. Same thing between this point in here, there is no current flowing, so it should be reading 0. So that is the distinction between the delta V and the IR. The IR depends on I, and the delta V depends on where you're measuring it. If you're measuring it across a battery, then definitely the battery has a fixed value in that case. If you're measuring it across a resistor, then in that case, you're going to get 0. So these are some of the distinction between them. Some of this advantages of this device, you could end up with higher currents in this scenario in here. So you could end up with a higher current. Okay. So that's a good thing. So if you're really desiring to have higher current, it's a good idea to have that. But in here, no, actually, sometimes it's not good to do that. So you have to be careful in this case because you would want a higher voltage across the device itself. So how am I going to say it? Actually, in here, you don't want the higher current because that will lead to a higher power. As a matter of fact, you notice that when you put them in parallel, and the more, in series, the more you put them, the light dims. So in this case, you're consuming less power per light bulb, okay? So in this case, the power consumption is less. Per device. So in other words, if you have a device that is sensitive enough and you would want to protect it, and it's supposed to only have so much power, you could put a big resistor next to it. So that's important. So there is an advantage in here. So for the series, so you can't just discount it just because you really want higher currents. So if you put them in parallel, then that device isn't protected. So if there is a device that's supposed to consume only 5 watts, and all of a sudden you put it in parallel and you put a huge voltage across it, so it's going to burn it and you're going to smell smoke, actually, and you're going to see the smoke rising in there. So you have to be very careful with this thing. So what you do in this case, you put next to it a big resistor. That resistor will tame the current enough so that there is not a lot of current flowing through that device. So it's going to be something that's how you want it. So again, that's why in a given circuit, you will have all kinds of things in here, because at some point you would want the whole thing to be tamed with a resistor. Some other times you would want you would want a capacitor to take the charges. So, typical devices in a circuit are far more complicated, and they have all kinds of other things also involved with them, because the way they store charges, the way they handle current, the way that they handle, so they have all kinds of things. So I mentioned few of them so far. But in this class, you're only supposed to be concerned with the resistors at this point. If you take the second physics, the calc-based physics, or there is another physics also for the medical students, physics 150, the 150 series, that is 151 and 52, then you're going to deal with electricity, and you're going to discover other devices, for example, capacitors, which are an important device. They store charges, they store energy. Also inductors. Inductors are useful in terms of transformers, which are very, very important component. Because if you look, for example, of your computer, for example, it's supposed to support what, 19 volt, 20 volts. But the power company delivers to your household 120. So you'd want to bring 120 down to where your computer works. As a matter of fact, the power company delivers to the outside of your place more than 120 volt to delivers a huge amount of voltages, and there is a huge transformer outside of your place, wherever you are, or even in business, that brings the current down to something that is manageable, and even brings it down to 120 volts to come to your plug. And even then, when you connect your cell phone trying to charge it, or you need something to bring it even further. So these are called drop-down transformers versus a step-down transformer versus step-up transformers, which they work with a power company to deliver higher and higher voltages so that they deliver the power to where you are. Again, the topic is very, very, very big. It has a lot of details in it, whether how the power is made. We make power using the alternating current, which we did not really discuss it much at all in here. I know I mentioned it briefly here, and I mentioned it also in the lab. But the AC current, actually, these devices work, especially this one, work with the AC current more. No, not more. It works exclusively with the AC current. When we talk about the transformers, transformer will not work with the with the DC currents. So alternating current versus direct current. So it works only with the alternating current of those devices. So again, the power itself is actually created in an alternative fashion. And I know we didn't really go into detail to Faraday's law and all of the other interesting stuff, but we're going to discuss some more stuff coming down the road on magnetism, and we will have in-depth discussions. Now, this is not the end of electricity. We still have magnetism, of course. We still have also other assignments, and homework assignments are going to be deferred after the exam, so that your focus is right now is on the exam. Please reach out if you have any questions, if you have difficulties. I tried to make this session as probably as light as I could in terms of content. I know I gave a lot of examples, and I focused only on the example we did in the lab. But if you guys need more applications, let's wait until after the exam, then we will definitely have more of those. Thank you, guys. Let me stop sharing. Oh, yeah. Okay. Thank you.